The universe runs on rules, but sometimes it seems to break them. We are about to journey through 25 of the most baffling glitches in the fabric of reality itself, from silent signals from the void to galaxies moving toward something we cannot see. By the end, you will understand just how much of the cosmos remains a brilliant, beautiful mystery. We will encounter a star that dims in impossible ways, and a void so vast it rewrites the story of our place in space. What single cosmic anomaly makes you question everything you think you know? Our first mystery begins with a pair of robotic explorers, the Pioneer 10 and Pioneer 11 spacecraft. These were humanity's first emissaries to the outer planets, and later, the first human-made objects on a trajectory to leave our solar system entirely. Yet as they sailed into the interstellar dark, scientists tracking their precise paths noticed something deeply wrong. The spacecraft were slowing down. Not from hitting anything, not from a mechanical failure, but from an unseen, persistent tug pulling them back toward the sun. It was a deceleration so slight you would never notice it in daily life, a deviation smaller than a nanometer per second squared. But over the vast distances of space, this tiny, unaccounted-for force added up, throwing their predicted positions off by hundreds of thousands of kilometers. This was the Pioneer anomaly. For decades, this minuscule drift haunted the world of celestial mechanics. The laws of gravity, as described by Einstein and Newton, had predicted their paths with incredible precision for everything else. So what was acting on these two lonely probes? The immediate suspicion fell on the spacecraft themselves. Perhaps it was thermal radiation pressure, the gentle but constant push from heat radiating off their nuclear power sources and electronics. Like a car with its parking brake slightly engaged, this internal heat could theoretically provide just enough backward force to explain the drift. Other ideas pointed to more exotic possibilities, like a subtle flaw in our understanding of gravity itself over very large scales, or even the gravitational influence of unseen, diffused dark matter within our solar system. The mystery persisted because it was so hard to test. The Pioneers were simple, spin-stabilized craft, not designed for ultra-precise navigation physics experiments. Their data was old, their signals grew faint, and eventually they fell silent. For years, the anomaly stood as a tantalizing hint that our cosmic rulebook might have an unread footnote. Then, through painstaking analysis of decades-old telemetry and sophisticated new thermal models, a consensus emerged. The most likely culprit was indeed the spacecraft's own heat. Asymmetric radiation from their warm bodies was giving them that tiny, constant push backward. This explanation, while elegant, still has its skeptics. Some argue the thermal models cannot fully account for the entire effect. So while the case may be largely closed for the Pioneer probes, the episode serves as a profound lesson. It shows how the quest to understand a tiny glitch in the data can force us to examine every possible variable, from the warmth of a circuit board to the fundamental nature of the universe itself. It was a whisper from the void that made us listen more carefully to everything. But the whispers of cosmic rule breaking did not end with the drifting Pioneers. A different, more fleeting anomaly emerged from a routine spaceflight maneuver, one designed to save fuel and time. It is called the gravity assist or planetary slingshot. The principle is elegant, a celestial billiard shot where a spacecraft steals a tiny fraction of a planet's orbital momentum to fling itself faster toward its destination. We have used this trick for decades, and our calculations for these flybys are normally a masterpiece of precision. Yet on several key missions, something went subtly, inexplicably wrong. As spacecraft like Galileo, Near, and Rosetta swung past Earth for a gravity boost, deep space tracking stations measured their resulting speeds. Each time, the spacecraft gained a tiny, extra burst of velocity that our best models could not account for. This is the flyby anomaly. The discrepancy was minuscule, often just a few millimeters per second added to their speed. To put that in perspective, it is far less than the speed a snail moves. But in the hyper-precise realm of orbital mechanics, where an error of a single millimeter per second can mean missing a distant asteroid by thousands of kilometers over years of travel, this was a glaring problem. It was as if the universe was giving these probes an unexpected, secret push on their way out the door. The strangest part was its inconsistency. The anomaly did not happen every time. Some flybys matched predictions perfectly, while others, like the Rosetta spacecraft's Earth flyby in 2005 and 2007, showed this unexplained speed boost. This made it even more perplexing. If our math was fundamentally wrong, you would expect the error to show up consistently. The fact that it did not pointed to something more situational, perhaps a hidden variable we had not considered. Theories to explain it range from the subtle to the revolutionary. Some scientists have suggested that Earth rotation might create a slight, unforeseen frame-dragging effect, warping space-time around the planet in a way that gives passing objects an extra nudge. Others look to more exotic ideas, like a local halo of dark matter around Earth whose gravitational influence we have not mapped. There is even a fringe but fascinating proposal related to inertia itself, suggesting that the way an object's inertia responds to acceleration might be very slightly different when it is moving toward the Sun versus away from it, a concept known as the modified inertia hypothesis. For mission planners, this anomaly is more than a curiosity. It is a genuine headache. Our ambitions are growing, aiming for precision landings on distant moons and complex multi-flyby trajectories to the outer planets. An unknown force that occasionally tweaks a spacecraft's speed by a tiny amount introduces an element of uncertainty into journeys that last for a decade or more. It means we might need to carry a little extra fuel for unexpected course corrections, fuel that is incredibly expensive to launch and limits what else a mission can do. The flyby anomaly remains an open case, a reminder that even our most trusted celestial tricks can still hold surprises. It tells us that space, even in our own celestial neighborhood, might still have pockets of subtle physics we do not yet understand, waiting to be revealed by the silent passage of a human-made object swinging past its home planet one last time. This unsettling sense of a cosmic rulebook with missing pages only deepens when we look at the oldest light in the universe. After the Big Bang, the newborn cosmos was a searing, opaque plasma. As it expanded and cooled about 380,000 years later, light finally broke free. That first flash of liberation has been traveling for over 13 billion years, stretched and cooled by the expansion of space into a faint microwave glow that permeates every corner of the sky. This is the cosmic microwave background, and it is our most precise snapshot of the infant universe. We expect this ancient afterglow to be almost perfectly uniform, a testament to the universe's fundamental fairness. The tiny temperature fluctuations we see, mere millionths of a degree, should be random like static on an old television screen with no preferred direction or special alignment. This expectation is rooted in a cornerstone idea called the Copernican principle, the notion that we do not occupy a special or privileged place in the cosmos. The universe on the largest scales should look roughly the same in every direction. But when scientists created exquisitely detailed maps of this microwave background, they found something that sent a chill through cosmology. The fluctuations were not completely random. They appeared to show a strange alignment, a subtle pattern that seemed curiously linked to the plane of our own solar system and the direction of Earth's motion through space. Researchers with a hint of dark humor named this alignment the axis of evil. The name captures just how cosmologically unsettling it is. Finding a preferred direction in the universe's oldest light is like discovering that the foundation of a building is slightly tilted in a way that points directly to your front door. It suggests, against all our foundational beliefs, that we might indeed be in a special place, that the universe has a large-scale structure that somehow knows about the orientation of our little solar system. This is profoundly disturbing for the standard model of cosmology. If the axis of evil is real and not a statistical fluke or a data processing artifact, it implies that the universe is not isotropic, not the same in all directions on the grandest scales. It could mean our entire observable universe is just a patch of a much larger, lopsided cosmos, or that something in our local environment is contaminating the signal in a way we do not yet understand. The most conservative explanation, and the one many hope is true, is that it is a trick of the data. Perhaps it is an unresolved foreground effect, like faint emissions from dust within our own Milky Way galaxy that were not perfectly subtracted from the maps. Or maybe it is a subtle systematic error in the incredibly complex instruments on satellites like Planck, which gathered this magnificent data. For over a decade, teams have been combing through the measurements, applying new corrections and analyses, trying to make the anomaly disappear. Yet, stubbornly, some signature of it remains in the data. Its persistence is what keeps cosmologists awake at night. It represents a quiet but persistent crack in the foundation of modern cosmology, a whisper from the ancient light that the universe might be more strange, more structured, or more intimately connected to our local frame of reference than we ever dared to believe. The quest to solve it is a monumental exercise in humility, forcing us to question whether the anomaly is in the sky or in our own unblinking gaze. If the ancient light of the cosmos holds a secret alignment, then the motion of its greatest structures suggests a destination. Across the unfathomable dark, entire clusters of galaxies are racing, not in the random, gentle drift of cosmic expansion, but in a powerful, coordinated stream toward a single point on the sky, a place far beyond the edge of everything we can see. This is the dark flow, and it is perhaps the most direct challenge to our understanding of the universe's boundaries. The discovery came from studying the most massive objects in existence, galaxy clusters, which contain thousands of galaxies swimming in a sea of superheated gas. Scientists used a subtle trick of physics called the kinetic Sunyaev-Zeldovich effect. Here is how it works in simpler terms. The cosmic microwave background, that ancient afterglow from the Big Bang, fills all of space. When a massive galaxy cluster moves through this sea of light, the hot electrons within its gas give the passing microwaves a tiny energy boost, like a swimmer creating a slight wake in still water. By measuring this incredibly faint distortion in the background radiation, astronomers can calculate not just that a cluster is moving, but precisely how fast and in what direction. When researchers applied this technique to hundreds of clusters, they expected to see a random scatter of motions, the local jostling within the grand, smooth expansion of the universe. Instead, they found a shocking consensus. Clusters spread across billions of light years were all streaming toward the same patch of emptiness, at speeds exceeding 2 million miles per hour. This was not a local phenomenon. The scale was too vast, the coherence too perfect. It was as if every continent on Earth was slowly, irresistibly sliding toward a single spot in the Pacific Ocean. The force required to tug these unimaginably heavy conglomerates of stars and dark matter must be titanic, far beyond the gravitational pull of anything within our observable universe. The only plausible explanation is that the source of this pull lies outside of it, beyond our cosmic horizon. We are seeing the gravitational shadow of something truly colossal, a structure or mass so immense that its influence leaks into our pocket of space-time. This idea shatters the conventional view that the universe is all there is. It implies our entire observable cosmos, over 90 billion light-years across, might be just one island in a much greater archipelago of reality, and that some neighboring island is so massive we can feel its tide. What could possibly exert such a pull? Theorists venture into breathtaking speculation. One possibility is that the dark flow is evidence of other universes in a vast multiverse, and we are feeling the gravitational tug of a neighboring cosmos brushing against our own. Another, even more profound idea is that this flow is a relic from before the Big Bang, a remnant imprint from an earlier phase of reality whose structures still guide the motion of our universe like deep ocean currents. It suggests our cosmic beginning might not have been a clean, isolated event, but part of a longer, older story we are only now glimpsing through the collective drift of galaxies. The dark flow remains controversial. Some argue the signal could be a systematic error, though subsequent studies with new data have continued to support its existence. Whether a flaw in our measurements or a flaw in our cosmic map, its implication is staggering. It paints a picture of a universe that is not alone, not self-contained, but potentially part of a deeper, darker, and infinitely larger geography. We are left watching the galaxies stream toward a horizon we cannot see, toward a mystery that redefines the very meaning of outside. Yet this mysterious flow is not the only force guiding our cosmic journey. Closer to home, within the grand tapestry of our observable universe, we find ourselves caught in a more local but equally powerful tug of war. For decades, astronomers knew our Milky Way and its neighboring galaxies, a cluster called the Local Group, were not drifting aimlessly. We were all racing toward a specific point in the constellation Centaurus at a staggering 1.5 million miles per hour. The source of this immense pull was dubbed the Great Attractor. Picture a gravitational sinkhole in intergalactic space, a region of such concentrated mass that it draws entire galaxies into its orbit. The problem was we could not see it. The plane of our own Milky Way, thick with stars and dust, lies directly in the line of sight, obscuring our view like a cosmic mountain range hiding a distant valley. It was a massive, invisible something pulling us toward the unknown. For years, the Great Attractor was a profound embarrassment. How could we map the cosmos if a hidden monster was distorting the very map we were trying to make? The breakthrough came with new tools that could peer through the galactic dust, using X-ray telescopes and infrared surveys to see what visible light could not. They revealed not a single monstrous object, but an immense confluence of mass known as the Norma Cluster, a dense knot of galaxies and, crucially, the unfathomable amounts of dark matter surrounding it. This entire complex, including the nearby Centaurus cluster, forms the core of the gravitational anomaly we call the Great Attractor. It is not a mysterious new force, but the collective pull of hundreds of thousands of galaxies in a region of space over 500 million light-years across. Our motion is part of a vast cosmic river with countless galaxy groups all flowing toward this same dense supercluster, but the story of our motion does not end with a pull. Every action in the universe has an equal and opposite reaction, and our journey is shaped just as much by what is pushing us as by what is pulling. Scientists realized that to fully explain the speed and direction of our local group's travel, they needed to account for both the gravitational attraction from dense regions and the lack of attraction from empty ones. Enter the dipole repeller. While the Great Attractor is a mountain of mass, the dipole repeller is a profound valley, a vast and staggeringly empty region of space spanning nearly 2 billion light-years. In this cosmic void, the density of galaxies is so low that its gravitational influence is effectively negative. It is not actively pushing matter away like some anti-gravity field, but rather it is failing to pull. With so little mass inside it, the expansion of the universe has more relative effect, causing galaxies on its edges to be pushed away from the void and toward denser regions. Think of it like a ball rolling down a hill. The ball is pulled by gravity toward the bottom, the dense valley, but it is also, in a sense, being pushed away from the flat, high plane it started on because there is nothing there to hold it back. Together, the Great Attractor and the dipole repeller sculpt our path. We are being pulled toward the immense mass concentration in one direction and simultaneously pushed from behind by the expansive emptiness in the other. Mapping these structures is the ultimate exercise in cosmic cartography, where you must chart not just the bright islands of galaxies, but the profound depths of the dark seas between them. It is a reminder that in the grand scheme of the cosmos, emptiness holds as much sway as fullness. Our galaxy's journey is a delicate dance between the seen and the unseen, between the mountains of light and the valleys of nothing, forever caught in the balance of attraction and repulsion on the largest scales imaginable. The gravitational push and pull we feel is not the only way our cosmic neighborhood stands out. We reside in a bubble, but not one made of air or light. Our galaxy, along with our entire local group, floats in the center of an immense spherical region of space that is staggeringly empty. This is the KBC void, named for the astronomers who identified it, and it is a hole in the universe on a scale that defies easy belief. Spanning a diameter of roughly 2 billion light-years, this void is not just a bit less crowded. It is a cavern of profound nothingness where the density of galaxies, clusters, and matter is about 20% lower than the cosmic average. To find our home galaxy sitting in the middle of such a vast emptiness is cosmologically shocking. It directly challenges a bedrock assumption called the cosmological principle, which states that on the largest scales, the universe should be smooth and homogeneous like a well-mixed batter. No single place should be noticeably special, yet here we are in the center of the largest cosmic void we have ever identified, a clear and dramatic deviation from that smoothness. The statistical odds of this are mind-bending. Think of it like this: you sprinkle a handful of sand evenly across a vast floor. The cosmological principle says that if you zoom out far enough, the floor should look uniformly sandy. Now imagine you discover that one particular grain of sand, by pure chance, landed in the exact center of the only perfectly circular, sand-free patch on the entire floor, a patch that itself is enormous. That is our situation with the KBC void. The sheer scale of this emptiness makes it a profound anomaly. It is not just a curiosity of our location, it has real, measurable consequences for how we see the universe. Because we are inside this bubble of lower density, the space around us is expanding at a slightly faster rate than the cosmic average. There is simply less gravity here to slow things down. This local faster expansion affects how we measure the universe's expansion rate, a number called the Hubble constant. When we use nearby objects like supernova in our galactic neighborhood, we are measuring expansion from inside this fast-moving bubble. But when we look at the ancient cosmic microwave background, we are measuring the universe's expansion from a time long before such structures existed. The fact that these two methods give stubbornly different results, known as the Hubble tension, might be partially explained by our residence in the KBC void. Our local cosmic address could be skewing our perspective, making our corner of space appear to be expanding faster than the universe as a whole. The void forces a humbling realization. We have long assumed we lived in an average place because to assume otherwise seemed arrogant, but the cosmos appears to have placed us in a position of extreme statistical rarity at the heart of a great cosmic nothing. This does not just change our address, it changes the calibration of our entire map of reality, suggesting that to truly understand the universe, we must first account for the extraordinary emptiness that surrounds us. Our residence in a cosmic void might explain part of a far greater and more pressing mystery, one that threatens to unravel our entire understanding of cosmic history. This is the Hubble tension, a stubborn and growing disagreement over how fast the universe is expanding right now. The problem is not that we do not know the number, it is that we keep getting two very different yet seemingly correct answers. One answer comes from looking at the ancient universe, specifically the cosmic microwave background. By analyzing the intricate patterns in that baby picture of the cosmos, scientists can calculate how fast the universe should be expanding today, following the known laws of physics. This method gives us a very precise value. The other answer comes from looking at our modern local universe. We measure distances and speeds of nearby stars and, most importantly, a special kind of exploding star called a Type 1, a supernova. These supernovae are cosmic mile markers, their known brightness allowing us to gauge vast distances. By watching how fast galaxies containing these supernovae are moving away from us, we get a direct measurement of the current expansion rate. The local measurements consistently return a number that is significantly faster by about 10% than the prediction from the early universe. This is not a small margin of error. These are two of the most precise measurements in all of science, and they are in direct, glaring conflict. It is as if you carefully calculated how fast a car should be going based on its engine power and the hill it climbed, only to point a radar gun at it and find it is moving much quicker than your math allows. For years, astronomers hoped it was a simple mistake, perhaps a calibration error in a telescope or a subtle flaw in how we analyze the supernova data. But as measurements have improved with new telescopes like the James Webb Space Telescope, the discrepancy has not gone away, it has hardened. This is why it is called a tension. It is the strain between two pillars of modern cosmology that are slowly being pulled apart. The implications are profound. If both measurements are right, then our standard model of cosmology, which beautifully explains everything from the formation of galaxies to the abundance of light elements, is missing a crucial ingredient. Something must have changed the expansion history of the universe between that ancient afterglow and the stars we see today. Perhaps dark energy, the mysterious force accelerating the expansion, is not constant as we have assumed. Maybe it has been strengthening over time, giving the universe an extra push that our models did not account for. Other possibilities reach into the fabric of reality itself. Could there be new, unknown types of subatomic particles that flooded the early universe, subtly altering the physics of that first light? Or is our understanding of gravity itself incomplete on the largest scales? The Hubble tension is more than a technical disagreement, it is a potential crisis. It suggests that our cosmic story, from the Big Bang to the present, might have a hidden chapter, a twist in the plot that we have completely overlooked. Solving it will require either a revolutionary discovery or a humbling admission that one of our most trusted ways of seeing the cosmos is somehow deeply flawed. It is a reminder that the universe's greatest secrets are often hidden not in the distant anomalies, but in the plain numbers that simply refuse to agree. This precise disagreement over cosmic expansion finds a strange parallel in a much older, quieter mystery, one written in the chemical signature of the universe's first stars. While the Hubble tension questions the speed of our universe's growth, another anomaly challenges the very recipe of its birth. According to our most detailed models of the Big Bang, the first few minutes of cosmic existence were a frenzied nuclear forge. As the newborn universe expanded and cooled from an unimaginable heat, protons and neutrons collided and fused, cooking up the primordial elements. This process, Big Bang nucleosynthesis, produced the lightest elements in a very specific ratio, mostly hydrogen, a good amount of helium, and trace quantities of deuterium and one particular isotope, lithium-7. The calculations for these abundances are a triumph of modern physics. They depend on fundamental constants like the density of ordinary matter and the expansion rate of the early universe. The predictions for hydrogen, helium, and deuterium match the amounts we observe in the oldest, most pristine celestial objects almost perfectly, but lithium is the glaring exception. When astronomers point their telescopes at ancient stars in the halo of our galaxy, stars that formed from nearly pure primordial gas, they find only about 1/3 of the lithium-7 that the Big Bang models insist should be there. It is a deficit of roughly 2/3, a mismatch that has stubbornly persisted for decades despite ever more precise observations and refined calculations. This is not a minor accounting error, it is a fundamental discrepancy in the cosmic ledger. the lithium problem forces us to ask a profound question. Did our universe not cook its first elements quite the way we think it did? The search for an answer has led scientists down two very different paths. The first path looks for new physics in the early universe. Perhaps unknown particles like certain types of dark matter were present in those first fiery minutes. As they decayed, they could have altered the neutron-to-proton ratio or provided extra pathways for nuclear reactions, effectively destroying the fragile lithium nuclei as they formed. Another exotic idea involves theoretical particles called actions, which could have caused brief, localized heating in the primordial soup, disrupting the delicate fusion chain. The second path questions our understanding of the stars themselves. Maybe the ancient stars we use as cosmic fossils are not perfectly pristine. Could slow, internal processes over billions of years have gradually dragged lithium from their surfaces down into hotter interior layers where it was destroyed? Or perhaps our models of stellar astrophysics are missing a key ingredient like turbulent mixing that would naturally deplete surface lithium over time. The challenge is that both paths are fraught with difficulty. Invoking new particles is compelling but speculative, requiring evidence beyond this one anomaly. On the other hand, modifying stellar physics to destroy just the right amount of lithium without creating other inconsistencies in what we observe about these ancient stars has proven incredibly tricky. The lithium problem endures as a quiet but persistent thorn in the side of cosmology. It tells us that while our story of the universe's first 3 minutes is overwhelmingly successful, it may have a missing paragraph, one that involves either a subtle new particle or a misunderstood behavior of the oldest stars. It is a reminder that sometimes the most revealing clues about the dawn of time are not found in the grand sweep of galaxies, but in the faint spectral lines of a single ancient element that simply refuses to add up. The universe has a speed limit for light, but for the most energetic particles, it seems to have built a wall. This is the Greisen-Zatsepin-Kuzmin limit, or the GZK cutoff, a fundamental energy ceiling predicted over half a century ago. The logic behind it is beautifully simple, yet devastating for cosmic travelers. Space is not truly empty. It is filled with the faint, cold glow of the cosmic microwave background, the relic radiation from the Big Bang. When a proton, one of these ultra-high-energy cosmic rays, travels across the universe, it is not moving through a void. It is barreling through a sea of these low-energy photons. At a certain extreme energy threshold, something inevitable should happen. The proton gains enough energy that when it collides with one of these background photons, the interaction is no longer a gentle nudge. It becomes a catastrophic event, producing a shower of new particles like pions. This process robs the proton of a huge fraction of its energy, effectively putting a hard cap on how far such a particle can travel. Any cosmic ray proton with energy above this limit, about 100 million trillion electron volts, should be shredded by the microwave background within a relatively short cosmic distance, a few 100 million light-years at most. They should never reach Earth from the distant universe, yet they do. Our most sensitive observatories, like the Pierre Auger Observatory in Argentina, have repeatedly detected these ultra-high-energy cosmic rays, particles with energies far exceeding the GZK limit. They are incredibly rare, perhaps 1 particle per square kilometer per century, but their existence is undeniable. Each one carries the kinetic energy of a well-thrown baseball, packed into a single subatomic proton. The detection of these particles creates a profound paradox. If the GZK limit is correct and our understanding of particle physics is sound, then these cosmic rays cannot have come from very far away. They must originate from within our local cosmic neighborhood, within that few 100 million light-year radius. But when astronomers scour that region of space for a suitable source, a cosmic particle accelerator powerful enough to launch a proton to such insane energies, they find nothing obvious. No nearby active galactic nucleus is pointed directly at us. No cataclysmic galaxy merger seems to be in the right place. It is as if someone is firing a cannon in our backyard, but we cannot find the gun. This forces a troubling either-or dilemma. The first possibility is that these particles are indeed coming from nearby, but from sources we have not yet identified or understood. Perhaps there are exotic, hyper-efficient accelerators hidden in plain sight, like certain types of neutron star mergers or jets from quiet black holes, operating in ways our current models do not predict. The second, more radical possibility is that our understanding of particle physics at these extreme energies is incomplete. Maybe protons interact with the cosmic microwave background in a slightly different way than our standard model predicts, allowing them to survive their long journey somewhat intact. Or perhaps these are not protons at all, but heavier atomic nuclei, which would change the interaction calculations, though even that does not fully resolve the mystery. Some theorists have even ventured into the realm of new physics, suggesting the involvement of hypothetical particles like magnetic monopoles or defects in spacetime itself. The GZK paradox is a clash between an elegant theoretical prediction and a stubborn observational fact. It tells us that the most energetic events in the cosmos are either happening mysteriously close to home, or that the rules governing matter at the very edge of possibility are not quite the rules we have written down. It is a limit that the universe itself appears to be breaking, sending fragments of impossible energy our way, challenging us to find the source or rewrite the laws. Even as we grapple with cosmic speed limits and ancient chemical deficits, a different kind of signal once pierced the static, a whisper so perfect it seemed to speak directly to our deepest hopes. On a hot August night in 1977, a radio telescope at Ohio State University known as the Big Ear was engaged in its routine, monotonous work. It was slowly scanning the sky, listening to the constant hiss of the cosmos across a narrow band of frequencies near the hydrogen line, a quiet channel scientists reasoned might be used for interstellar communication. The data was printed out line by line on simple computer paper, a string of letters and numbers representing signal intensity. For days, nothing but the expected background noise. Then, just after 11:16 p.m., the telescope's feed recorded something extraordinary. For 72 seconds, as its beam passed a point in the constellation Sagittarius, the signal surged in strength, peaked, and then faded away exactly as expected for a celestial source moving with the rotation of the Earth. The sequence of characters printed was 6EQUJ5. Each character corresponded to a rising and falling intensity, a clean, powerful, narrowband radio burst. When volunteer astronomer Jerry Amon reviewed the data printout the next day, he was so stunned he circled the sequence in red pen and wrote a single, emphatic word in the margin. Wow, that annotation gave the signal its famous name, and its perfect profile gave scientists a profound shock. It matched precisely what theorists had predicted for an artificial signal from another star system. It was narrowband, meaning it was focused on one specific frequency. Unlike the broad spectrum noise of natural cosmic objects, it appeared and disappeared with the telescope's motion, confirming it came from a fixed point in space. And it was incredibly strong. For those 72 seconds, it was the loudest thing in the sky. The immediate, frantic search for a repeat began. Astronomers pointed every available instrument at that patch of sky for months, then years. They listened for decades, nothing, not a whisper, not an echo. The wow signal was a one-time event, a cosmic door that slammed shut as suddenly as it opened. The lack of a repeat is what makes the mystery so enduring and so tormenting. If it was a deliberate beacon from an intelligence, why would it transmit only once? If it was a natural phenomenon, what could possibly produce such a pristine, artificial-looking signature? The leading natural explanation points to hydrogen. In 2016 and 2017, an astronomer proposed that the signal could have been caused by a cloud of hydrogen surrounding a passing comet, two of which happened to be in that region of the sky at the time. As the comet's hydrogen reflected sunlight, it could, in theory, produce a radio emission at the right frequency. This hypothesis is compelling, but it is also heavily contested. Critics point out that comets are not known to emit such strong, narrowband signals, and the specific frequency of the WOW signal was protected from terrestrial transmission, making a simple human-made satellite or aircraft bounce unlikely. The signal's singular nature protects its mystery. It exists as a flawless data point, an event that passed every test for an artificial interstellar signal, except the one we cannot control: repetition. It stands alone in the history of the search for extraterrestrial intelligence, or SETI, as the one signal we cannot explain away, the one that got away. It is a reminder that the universe is capable of producing moments of startling clarity, brief windows where the static parts and something that looks like a message comes through, only to leave us forever wondering if we were ever truly being called. The search for a single, perfect signal has given way to a universe crackling with countless others, each a fleeting scream of raw energy. These are fast radio bursts, or FRB, and they are rewriting the book on cosmic cataclysms. Discovered only in 2007, these events are astonishingly brief, lasting mere milliseconds. In that eye blink of time, a single burst can release more energy than our sun puts out over 80 years. For years after the first one was spotted in archival data, they were considered rare and mysterious oddities, perhaps one-off explosions from unimaginably violent events. The true shock came when astronomers found one that repeated. This was not the death cry of a star, but a beacon that could flash again and again from the same spot in the void. Suddenly, the mystery multiplied. What natural phenomenon could both destroy itself in a titanic blast and then live to do it over and over? The hunt for an explanation has become a cosmic detective story with a growing list of suspects. The prime natural candidate is a type of ultramagnetic neutron star called a magnetar. Imagine the core of a giant star crushed into a city-sized ball, with a magnetic field so powerful it could erase a credit card from halfway to the moon. Theorists suggest that starquakes on the surface of these insane objects, or sudden rearrangements of their magnetic fields, could unleash focused beams of radio energy that sweep across space like a lighthouse. If that beam happens to point at Earth, we see a brilliant, fleeting flash. Another compelling idea involves catastrophic collisions, like two neutron stars spiraling together or a neutron star being torn apart by a black hole. Such events could produce a single, spectacular burst as a final farewell, but the repeating bursts demand a source that survives, pointing back to the magnetar or perhaps to a neutron star in a highly elliptical orbit around a companion, experiencing periodic, violent interactions. Yet, the sheer power and bizarre patterns of some bursts have inevitably led to more speculative thoughts. Could we be seeing leakage from unimaginably vast engineering projects? The concept of using focused radio beams to propel light sails across interstellar distances has been seriously proposed for our own future. A malfunction or a sweeping beam from such a system, operating on a galactic scale, might appear to us as a fast radio burst. While this is the least likely explanation for scientists, its persistence in popular thought highlights just how unnatural these natural events can seem. The mystery has only deepened as our telescopes have grown more powerful. We have now traced hundreds of these bursts back to their host galaxies, often billions of light years away. The results are a cosmic Rorschach test offering no single answer. Some bursts come from ancient, quiet galaxies where star formation has long since ceased. Others erupt from young, turbulent galaxies ablaze with stellar birth. A few have even been traced to the spiral arms of galaxies, much like our own Milky Way. This diversity is frustrating. If all FRBs came from one type of galaxy, we would have a crucial clue. Instead, the universe seems to be telling us that the conditions to create these immense flashes can arise almost anywhere under many different circumstances. It suggests that the engine behind them, whether it is a magnet or something else, is a common ingredient in the cosmic recipe, yet one that operates in ways we are only beginning to glimpse. Each new detection is a piece of a puzzle we are still assembling, a reminder that the cosmos is not only stranger than we imagine, but more energetic, more repetitive, and more brilliantly cryptic than we ever dreamed. The universe speaks in bursts of energy and in silent, tumbling stones. In the autumn of 2017, our solar system received a visitor from the depths of interstellar space. For the first time in recorded history, we witnessed an object that was not born here. Telescopes on Hawaii gave it a name that means scout or messenger from afar arriving first, Oumuamua. It was already speeding away when we spotted it, a faint dot of light receding into the void. But in that brief window of observation, this cosmic messenger revealed a series of traits so bizarre they ignited a firestorm of scientific debate. First was its shape. By analyzing how its brightness changed dramatically as it tumbled, astronomers deduced it was not round, not even lumpy, but profoundly elongated. Its length was estimated to be up to 10 times greater than its width, a shape like a cigar or a pancake tumbling end over end through the dark. This alone was strange. Most solar system objects, after billions of years of collisions and gravitational interactions, are roughly rounded. Such an extreme shape suggested this object was either very young or forged in a process we do not commonly see. Then came the second puzzle, its silence. Oumuamua showed no coma, the fuzzy halo of gas and dust that surrounds comets as they approach the sun and their ices vaporize. It looked like a bare, inert rock, an asteroid, yet its trajectory told a different story. As it hurtled away from the sun, its path could not be explained by gravity alone. Something was giving it an extra tiny push, a non-gravitational acceleration. For comets, this is common, caused by jets of vaporizing ice acting like natural rocket engines. But Oumuamua displayed no visible outgassing, no dust tail, no coma. It was accelerating in silence as if propelled by an unseen force. This combination of traits, the strange shape and the stealthy acceleration, demanded explanation. The scientific community scrambled for natural answers. One compelling theory proposed it was a hydrogen iceberg. In the cold, dense cores of giant molecular clouds, solid hydrogen could form. Such an object would sublimate, turning directly from solid to gas under the sun's warmth, providing thrust without leaving a dusty trail we could see. The problem is that a hydrogen iceberg is incredibly fragile, likely unable to survive a journey of millions of years through interstellar space. Another idea suggested it was a fragment of a Pluto-like world, a chunk of solid nitrogen ice sheared off by some ancient impact. As nitrogen sublimated, it could provide the thrust, and the object would naturally erode into an elongated shape. This, too, is speculative, requiring a very specific and violent history. The sheer oddity of the object, however, led one prominent astronomer to voice a more provocative hypothesis. Could Oumuamua be artificial in origin? Specifically, debris from an advanced light sail, a thin sheet of material designed to be pushed by starlight. This would explain the extreme thinness and the non-gravitational acceleration, as sunlight itself would push on such a structure. It would also explain the lack of outgassing or a tail, as there would be no ice to vaporize, just reflective material. This suggestion was not a declaration of discovery, but a challenge to consider all possibilities, however unlikely. It underscored how Oumuamua's characteristics fell just outside the boundaries of every comfortable category we have. The fundamental frustration is that we will never know for sure. By the time we saw it, it was already too far away for detailed imaging or a probing mission. Our data is limited to that brief, tantalizing light curve and trajectory. It came, it confounded, and it left. Oumuamua is now a permanent resident of the interstellar dark, carrying its secrets with it. Its visit was a humbling reminder that our solar system is not an island, that the galaxy is constantly passing debris through our backyard. And the next time such a scout arrives, we may be just as unprepared, left to decipher another set of impossible clues from a messenger that does not stop to talk. A cosmic visitor from beyond our solar system is one thing, but our own planet holds a paradox written in stone and water. Billions of years ago, when life first began to stir on Earth, the Sun was a different star. Astrophysical models tell us with great certainty that our young Sun was about 30% dimmer than it is today. It has been slowly brightening over its lifetime as the nuclear fusion in its core becomes more efficient. Under that faint, pale sun, the Earth should have been a frozen snowball, a world locked in ice from pole to pole. The mathematics of climate are unforgiving on this point. Yet the geological record screams the opposite. Some of the oldest rocks we find, like the 3.8 billion-year-old Isua supercrustal belt in Greenland, show clear signs of having been shaped by liquid water. There is evidence of ancient riverbeds, sedimentary layers, and minerals that can only form in the presence of liquid water. This is the faint young sun paradox. How could a planet orbiting a weaker star have been warm enough for oceans to flow, for the cradle of life to be filled, not frozen? The leading answer points to the planet's own atmosphere acting as a blanket. Today, we worry about the greenhouse effect from carbon dioxide trapping too much heat. For the early Earth, scientists propose we needed a much thicker, more potent blanket. The prime suspects are greenhouse gases like carbon dioxide and methane, which could have been present at levels hundreds or even thousands of times higher than they are today. A dense, hazy atmosphere rich in these gases could have trapped enough of the sun's feeble warmth to keep the global thermostat above freezing. This solution, however, creates new puzzles of its own. The required amounts of carbon dioxide are staggeringly high. When scientists run climate models with enough carbon dioxide to offset the faint sun, they often produce a world that is not just warm but scorching, with surface temperatures far exceeding what the geological evidence suggests. Furthermore, the mineral record itself argues against it. Ancient soils and marine sediments show chemical signatures that imply carbon dioxide levels, while higher than today, were not nearly high enough to solve the paradox alone. This has forced planetary scientists to look for other warming agents, other threads in the atmospheric blanket. Methane, produced by early microbial life, is a powerful contender. A methane-rich haze could have provided significant warming, but methane is fragile in the atmosphere, broken down by sunlight unless it is constantly replenished. Another fascinating idea involves nitrogen. A much thicker atmosphere overall, primarily of nitrogen, would create higher surface pressure. This pressure broadening effect would allow other greenhouse gases to absorb heat more efficiently, like turning up the weave on the blanket. Some researchers even look to completely different mechanisms, like a slower rotation of the early Earth, leading to different cloud patterns that trapped heat more effectively. The faint young sun paradox is not just about ancient history, it is a masterclass in planetary systems. It teaches us that a planet's climate is a delicate balance between the light it receives and the air it breathes, a balance that can be maintained in multiple, surprising ways. Solving it is crucial not only for understanding our own origins, but for interpreting the potential for life on distant worlds orbiting other faint young stars. The paradox reminds us that a warm, wet world can exist under a cool sun if the chemistry of its sky is just right. The faint sun paradox reveals how a planet's atmosphere can rewrite the rules of climate, but Saturn's north pole shows us that the sky itself can defy geometry. There, whirling within the perpetual darkness of the gas giant's northern winter, is a structure of impossible perfection. It is a hexagon, a six-sided jet stream of hurricane-force winds, each side longer than the diameter of Earth. For over 40 years, through multiple spacecraft visits and Earth-based observations, this colossal geometric storm has held its shape, a 20,000-mile-wide monument to atmospheric mystery. The discovery came from the Voyager flybys in the early 1980s. As the probes sped past, their cameras captured a glimpse of something utterly unexpected at the North Pole. Instead of a swirling vortex like the one found at Saturn's South Pole, or like the eye of a hurricane on Earth, they saw sharp, clean angles. It looked less like a natural weather pattern and more like a feature etched by some cosmic machine. Decades later, when the Cassini spacecraft arrived for a long-term stay, it confirmed the hexagon was not only still there but astonishingly stable. Cassini's infrared and visible light cameras peered through the haze, revealing that this hexagonal jet stream acts as a towering wall of cloud, reaching deep down into the atmosphere. Inside its boundaries, the weather is chaotic, with smaller vortices spinning and churning. Yet the six-sided boundary itself remains crisp and unwavering, a perfect polygon drawn on a planet. Scientists turn to the laboratory to understand it. When a fluid rotates in a circular container and a smaller, central disk spins at a different speed, fascinating patterns can emerge in the fluid between them. Under the right conditions, these patterns are not random swirls but stable polygons with 4, 5, 6, or even 7 sides. This is a classic demonstration of fluid dynamics, showing how shear forces, the difference in speed between adjacent bands of moving fluid, can create standing wave patterns. On Saturn, the hexagon is believed to be a gigantic, natural version of this experiment. The jet stream itself is the fast-moving fluid, and some deeper, slower-moving layer of Saturn's atmosphere may act as the inner disk, creating the shear that stabilizes the six-sided wave. But knowing the basic recipe does not solve the mystery, it deepens it. Laboratory experiments produce shapes that flicker and change. Saturn's hexagon has persisted for decades, possibly centuries, locked in place on a planet with no solid surface to anchor it, a world of unimaginable turbulence where storms the size of continents routinely form and fade. The scale is also incomprehensible. Each side of the hexagon is a raging river of wind over 8,000 miles long, yet these immense lines are nearly straight, meeting at precise 120-degree angles. How does a fluid system on a planet where winds can blow at over 1,000 miles per hour maintain such geometric precision over such vast distances and for such an unthinkable length of time? The stability is the true enigma. Earth's jet streams meander and buckle, our largest storms dissipate in weeks. Saturn's hexagon is a permanent feature of its polar weather, surviving seasonal changes that last for years. This suggests the structure is rooted incredibly deep in Saturn's fluid interior, perhaps connected to fundamental planetary rotation in a way we have not yet modeled. Some theories propose that a three-dimensional standing wave propagating up from deep within the planet is what pins the hexagon in place, making it a kind of resonant fingerprint of Saturn's internal dynamics. Others wonder if the unique properties of Saturn's atmosphere, a blend of hydrogen, helium, and trace compounds, allow for this freakish stability. The hexagon stands as a breathtaking reminder that nature's artistry operates on a scale we are only beginning to appreciate, a perfect shape etched in the clouds of a giant, whispering secrets about the hidden flows that sculpt worlds. A star over 1,000 light-years away, KIC 8462852, became infamous for one simple reason: it could not keep its light steady. Known as Tabby's star after astronomer Tabitha Boyajian, who led its investigation, this otherwise ordinary star began to flicker in ways that defied all logic. Data from the Kepler Space Telescope revealed its light would dip, not by the smooth, predictable fraction caused by a planet, but in chaotic, dramatic plunges. Sometimes it dimmed by just 1%, other times by a staggering 22%, as if a colossal, jagged shape were drifting in front of it. These dips were also wildly irregular, with no repeating pattern that would indicate an orbiting body. It was a light curve unlike any seen before, a signature of something massive and misshapen blotting out the star's face. The immediate, frantic search for an explanation launched 1,000 theories. The leading natural candidate was a vast swarm of comets, perhaps the debris from a catastrophic collision in the star's own system. A giant cloud of dust and rock with clumps of varying density could theoretically create those irregular, deep dimmings, but the scale required was mind-boggling, needing millions of comets in a tight formation, a scenario that strained the limits of plausibility. Other ideas pointed to intrinsic stellar variability, but Tabby's star is not the right type of star for such violent tantrums. Its light output, when examined over a century of historical data, also showed a mysterious long-term dimming, as if the star itself was gradually growing fainter over decades. This combination of deep, random dips and a slow, secular fade was the one-two punch that made the mystery so profound. It was this strangeness that inevitably led to a more speculative, thrilling hypothesis. Could we be witnessing the construction of a Dyson sphere, or at least a swarm of megastructures built by an advanced civilization to harness their star's energy? The idea captured the public imagination because, for a brief moment, it fit the data. A partially built, lopsided array of solar collectors would create exactly the kind of bizarre, aperiodic shadows we were seeing. The scientific community, however, treated this not as a conclusion, but as a last resort, a possibility to be ruled out only after every natural explanation failed. And so, the world's telescopes turned toward Tabby's star. Subsequent observations across every wavelength, from ultraviolet to infrared, began to paint a more detailed, if still confusing, picture. The key clue came from the dimming itself. When a solid object like a planet or a megastructure passes in front of a star, it blocks all wavelengths of light equally. But when astronomers measured Tabby's star during a dip, they found it dimmed more in blue light than in red light. This is the telltale signature of dust. Tiny particles smaller than a grain of flour scatter blue light more effectively, letting more red light pass through. This finding was a major blow to the alien megastructure idea, as a solid swarm of collectors would not behave this way. The evidence strongly pointed to a natural obscuration by fine dust, yet solving one mystery only created another. What is producing this immense, chaotic cloud of dust? The comet swarm hypothesis remains on the table, but it is deeply unsatisfying to many. Some newer theories suggest we are seeing the aftermath of a moon being torn apart by its planet, or a giant impact between planet-sized bodies, creating a vast, evolving debris field that continues to occult the star in unpredictable ways. Others propose the dust is from the slow disintegration of a family of exocomets drawn in close to the star. The long-term dimming might then be caused by a vast, diffuse ring of this debris spreading out over the system. Tabby's star has quieted in recent years, its dramatic dips becoming less frequent, but the mystery is far from solved. It stands as a monument to cosmic curiosity, an object that forced us to confront the most extraordinary possibilities before guiding us reluctantly back toward natural chaos. It taught us that the universe can craft signals so odd they mimic intelligence, and that the truth, while likely written in dust, is still a story we have not fully read. A star's chaotic flickering is one thing, but the orderly motion of entire galaxies hides a deeper, more universal flaw. Every spiral galaxy, including our own Milky Way, spins like a vast celestial pinwheel. According to the laws of gravity established by Newton and refined by Einstein, stars orbiting on the outer edges of that pinwheel should move slower than those near the bright, dense core. The gravitational grip weakens with distance, so those distant stars should be lazily drifting along their orbital paths. Yet when astronomers like Vera Rubin began meticulously measuring the orbital speeds of stars in galaxies like Andromeda in the 1970s, they found something shocking. The stars far out in the galactic suburbs were not moving slowly at all. They were racing along, orbiting at nearly the same high speed as stars closer to the center. This was the galactic rotation curve anomaly, and it broke a fundamental rule. The visible galaxy, all the stars, gas, and dust we can see, simply does not contain enough mass to hold onto these speeding outer stars. At their velocities, they should have been flung off into intergalactic space long ago, like mud flying off a spinning tire. The only logical conclusion was that something invisible, something that does not emit or block light, must be providing extra gravity. This invisible gravitational glue holding fast-moving stars in their orbits is what we now call dark matter. Vera Rubin's work provided the most compelling evidence that galaxies are embedded within vast, diffuse halos of this mysterious substance, halos that extend far beyond the visible edge of starlight. Dark matter became the leading theory because it elegantly solved not just this one problem, but many others, from how galaxies cluster together to the patterns we see in the cosmic microwave background. It is the unseen scaffolding upon which the visible universe is built, but a theory that posits an entirely new form of matter, making up over 85% of the universe's mass, is a staggering proposition. It has led some scientists to ask a radical question. What if the problem is not missing matter, but a misunderstanding of the force itself? This is the premise of modified Newtonian dynamics, or MN. Proposed by physicist Mordechai Milgrom in the 1980s, MN suggests that our law of gravity, while extremely accurate here in the solar system, might work differently at the extremely low accelerations experienced at the edges of galaxies. In simple terms, gravity might not weaken with distance quite as sharply as Newton's law predicts when its pull becomes incredibly faint. A tiny tweak to the math could make those fast-orbiting outer stars behave exactly as we observe, without needing any invisible matter at all. The debate between dark matter and MN is one of the most profound in modern cosmology, and it is far from settled. Proponents of MN point out that it can remarkably predict the rotation curves of many individual galaxies from their visible mass alone, a feat dark matter models often struggle with unless they carefully tune the distribution of the dark halo. Supporters of dark matter counter that MN has major failures on larger scales, particularly in explaining the observed behavior of colliding galaxy clusters, where the gravitational effects clearly separate from the visible matter, something that strongly suggests a separate, invisible component. The collision known as the bullet cluster is often cited as a silver bullet against MN, as it shows gravity's lensing effect centered not on the galaxies themselves, but on clouds of hot gas that have been stripped away, a signature perfectly explained by dark matter but deeply problematic for modified gravity. Yet MN persists, evolving into more sophisticated theories. The tension forces us to confront a humbling possibility. Either the universe is filled with a ghostly substance we have never directly touched, a substance that outweighs everything we know 5-1, or our understanding of gravity, one of the most tested forces in physics, is subtly incomplete on cosmic scales. This is not a minor technical dispute, it is a fundamental choice between two radically different portraits of reality. The rotation of a single star at the edge of a distant galaxy thus becomes a fulcrum, balancing our entire conception of the cosmos. Dark matter may dominate the cosmic mass, but ordinary matter holds a census crisis of its own. According to the precise recipe of the Big Bang, the universe should contain a specific amount of normal atomic material, the protons and neutrons scientists call baryons. We can tally up the baryons we see in stars, galaxies, and glowing gas clouds, and the sum comes up short by a staggering 30 to 40%. An entire third of the ordinary stuff that makes up planets, people, and every visible thing is simply missing from our ledgers. This is not the mystery of dark matter. This is the puzzle of the missing baryons, a case of misplaced cosmic ingredients. The hunt for this lost matter has led astronomers to the most barren stretches of the cosmos, the immense voids between the great galactic filaments. Here, theorists predicted, the missing baryons would not be in bright clumps, but spread in a tenuous, superheated web known as the warm-hot intergalactic medium, or WIM. Picture the universe's large-scale structure as a sponge. The dense walls of the sponge are the galaxy filaments rich with stars. The holes are the vast voids. The WIM is the faint, hot gas that permeates the entire sponge, especially concentrated in the thinner strands connecting the dense walls. This gas is so diffuse and so hot, at temperatures of hundreds of thousands to millions of degrees, that it does not glow in visible light. It is essentially invisible, which is why it has evaded detection for so long. Finding something that does not emit light requires ingenious cosmic detective work. Astronomers use distant beacons like brilliant quasars as backlights. As the light from a quasar travels billions of light years to reach us, it passes through these invisible filaments of hot gas. The WIM, though incredibly thin, is not completely empty. It contains trace ions like oxygen 5 and 6 times ionized, meaning atoms stripped of most of their electrons. These ions can absorb very specific wavelengths of ultraviolet and X-ray light from the quasar's beam. By analyzing the quasar's spectrum, scientists look for the faint, telltale dips in brightness at those precise wavelengths. Each dip is like a fingerprint, a sign that the light has passed through a tendril of the missing matter. It is painstaking work, like trying to map a fog bank by the shadows it casts on a single, distant street lamp. Another technique involves looking for the WIM's own extremely faint glow in X-rays, or studying how it subtly distorts the cosmic microwave background through a phenomenon called the Sunyaev-Zeldovich effect. Each observation is a whisper, a hint that the missing matter is there, hiding in plain sight. The challenge is not just finding a few strands, but finding enough of them to account for that full 30 to 40% deficit. Recent surveys have begun to succeed, detecting enough of these filaments to suggest that the WIM likely holds the bulk of the missing baryons. This is a crucial discovery because it means our inventory of the universe is slowly becoming complete. We are not fundamentally wrong about how much ordinary matter the Big Bang produced. We just needed to learn where to look. The missing baryons were never truly lost. They were simply hiding in the dark, hot corridors of the cosmic web, waiting for our technology and cleverness to illuminate their ghostly presence. While the missing baryons hide in hot cosmic strands, a far more contentious anomaly was being pursued in a laboratory, promising to rewrite the rules of rocket science itself. The M drive, short for electromagnetic drive, was a concept so simple and so heretical it seemed like science fiction. A sealed, conical metal cavity, when filled with bouncing microwaves, was claimed to produce a tiny but measurable thrust, pushing in one direction without expelling any propellant whatsoever. This is a direct violation of Newton's third law, the conservation of momentum, a cornerstone of physics that states for every action, there must be an equal and opposite reaction. Rockets work by throwing mass backward to go forward. The M drive proposed to go forward by doing nothing more than bouncing light inside a can. The claim was not just improbable, it was physically impossible by all established understanding. Yet the experimental history is a fascinating saga of persistent, baffling signals. It began with a British inventor, Roger Scheuer, in the early 2000s. Small-scale tests in his lab reportedly showed a micronewton-level thrust, a force so small it is like the weight of a single grain of sand, but a force nonetheless. Then a team in China built their own version and reported similar results. The spark truly caught fire when a group at NASA Advanced Propulsion Lab Eagleworks took up the challenge. In a carefully controlled experiment in a vacuum chamber designed to rule out air currents and thermal effects, they too measured an anomalous thrust. The data was there, a whisper of force where there should have been nothing but silence. This triggered intense global skepticism from the physics community. The overwhelming consensus was that this had to be experimental error, an artifact so subtle it was masquerading as thrust. The leading suspect was thermal effects. As the cavity resonates with microwaves, it heats up unevenly. This thermal expansion could cause tiny shifts in the device's center of mass or interact with the test apparatus in a way that looks like a push. Another possibility was something called the Lorentz force, where stray electromagnetic fields from the device could be interacting with the Earth's magnetic field, creating a tiny but false thrust signal. Critics argued that the measurements were at the very edge of what the instruments could detect, buried in noise, and that no experiment had yet perfectly ruled out all these confounding factors. The controversy reached a peak when other labs around the world attempted to replicate it. Some, like a team in Germany, found that the thrust signal vanished when they accounted for a previously overlooked factor, the magnetic interaction between the power cables and Earth's field. Others reported ambiguous or positive results, but always with the caveat that systematic error could not be entirely excluded. The debate was never about dishonesty, but about the extreme difficulty of measuring an impossibly small effect. Proponents saw a hint of undiscovered physics, perhaps an interaction with quantum vacuum fluctuations, the seething sea of virtual particles that fill empty space. Could the drive be pushing off the fabric of spacetime itself? Skeptics saw a classic case of pathological science, where the desire for a breakthrough outruns the rigor required to kill a beautiful idea. The M-Drive's legacy is not a new engine, but a masterclass in scientific caution. It demonstrates how the siren song of an impossible result can drive years of meticulous, frustrating work, all to chase down a ghost in the data. It reminds us that sometimes the most exciting anomaly is not a doorway to a new universe, but a lesson in how carefully we must listen and how thoroughly we must doubt before we dare to declare that the laws of physics are broken. Deep within the heart of our own galaxy, a silent, invisible storm is raging. From the direction of the Milky Way's core, where a supermassive black hole named Sagittarius, a star, resides, telescopes have detected a mysterious and persistent glow. It is not a glow of visible light, but a torrent of high-energy gamma rays, the most powerful form of radiation in the universe. This is the galactic center excess, and its source has become one of the most tantalizing puzzles in modern astrophysics. The excess was first identified over a decade ago by scientists sifting through data from NASA's Fermi Gamma Ray Space Telescope. They were meticulously subtracting all the known sources of gamma rays from the region, things like supernova remnants, pulsars, and the diffuse background from cosmic rays interacting with gas. When all that familiar noise was removed, a distinct, unexplained signal remained. It wasn't a point source like a single star, but a diffuse, spherical halo of gamma-ray light centered on the galactic core, extending for thousands of light years. The energy signature of this excess was the key detail that set hearts racing. The gamma rays appeared at a very specific energy level, around a few giga-electronvolts. For physicists searching for dark matter, this was an electrifying clue. One of the leading theoretical candidates for dark matter is a class of particles known as weakly interacting massive particles, or WIMP. In regions of extremely high density, like the crowded center of a galaxy, these theoretical particles could occasionally collide and annihilate each other. The debris from that annihilation, according to many models, would include gamma rays at precisely the energy range Fermi was seeing. It was as if the universe had left a fingerprint at the scene of a crime, and it matched a sketch of our prime suspect. The galactic center, swollen with dark matter, could be the site where these ghostly particles are finally revealing themselves through their self-destruction. Yet extraordinary claims require extraordinary evidence, and the cosmos is a master of cosmic coincidences. There is a very compelling, more mundane explanation for the excess. The galactic bulge is an ancient, dense metropolis of stars. Within it could be a vast, hidden population of millisecond pulsars, the incredibly dense, rapidly spinning cores of dead stars. These objects are like cosmic lighthouses, beaming out powerful radiation, including gamma rays. Individually, they would be too faint for Fermi to resolve as distinct points against the bright background of the core. But collectively, thousands or even millions of them could blend together to create exactly the kind of smooth, spherical glow we observe. Distinguishing between these two possibilities, a dark matter signal or a pulsar fog, is a monumental technical challenge. It is the astronomical equivalent of trying to tell if a distant forest is made of dark, solid trees or a shimmering cloud of fireflies. The search for a smoking gun continues. If the excess is from pulsars, then next-generation radio telescopes or more sensitive gamma-ray observatories should eventually be able to pick out individual point sources from the haze, resolving the mystery into a crowd of familiar objects. If, however, the glow remains stubbornly smooth and diffuse as our observations improve, the case for a dark matter origin grows stronger. This is why the galactic center excess sits at a thrilling crossroads. It is a major goal for both particle astrophysics, which seeks to understand the fundamental building blocks of reality, and for traditional astronomy, which maps the stellar populations of our galaxy. Solving it could either unveil the first direct evidence of dark matter's particle nature, a discovery that would redefine physics, or it could reveal an entirely new understanding of stellar evolution and the frenetic life and death of stars in the galactic downtown. Either outcome changes our story, forcing us to rewrite a chapter about the hidden heart of our cosmic home. The search for dark matter's signature in the heart of our galaxy is a quest for hidden particles, but a far larger and colder shadow stretches across the ancient sky. Among the subtle temperature variations in the cosmic microwave background, one feature stands out with chilling clarity. It is a vast, circular patch of space, billions of light years across, that is significantly colder than the surrounding afterglow. This is the CMB cold spot, and its existence presents a profound cosmological riddle. The temperature difference is not enormous, only about 70 microkelvins colder than average, but its size and coherence are what make it statistically bizarre. Based on our standard model of the universe's structure and evolution, a feature this large and this cold should be exceedingly rare, a 1 in 50 event at best. Some analyses suggest the odds are even more remote, making it a glaring outlier in an otherwise statistically smooth cosmic baby picture. So what could possibly cast such a giant, frigid shadow on the dawn of time? The most conservative explanation is that we are simply seeing a rare but natural fluctuation, a colossal cosmic yawn in the infant universe. In a truly random distribution, even the most unlikely patterns will occasionally appear, and we might just be the unlucky observers who happen to live in a universe with one particularly large cold blob. While this is possible, many cosmologists find it unsatisfying, a statistical shrug that fails to explain the feature's peculiar profile. A more compelling, yet still natural, theory involves a cosmic texture defect. Imagine the early universe as a fluid cooling and crystallizing. Sometimes in the transition, defects can form in the crystalline structure like cracks or knots. A cosmic texture would be a specific type of topological defect, a tangled knot in the fabric of spacetime itself that formed during a phase transition just after the Big Bang. If such a texture existed within our observable universe and then unraveled, it would have injected energy into the surrounding plasma, creating a sort of gravitational hill. Photons from the CMB climbing this hill would lose a tiny amount of energy, making that region appear colder to us today. It would be a fossilized scar from a fundamental shift in the forces of nature. But the most breathtaking possibility is that the cold spot is not a feature of our universe at all, but a bruise from a collision with another. This idea stems from the theory of eternal inflation, which suggests our universe is just one bubble in a frothing, infinite multiverse. In this chaotic foam, other bubble universes could occasionally brush against or even collide with our own. The energy released in such a cataclysmic encounter would have been immense, but it would have happened during the inflationary period when our universe was expanding faster than light. The collision's aftermath would have been stretched to an unimaginable scale, imprinting a circular, temperature-modulated signature on the CMB, a cosmic kiss that left a permanent chill. Distinguishing between these ideas is the work of intense, ongoing analysis. Scientists are meticulously studying the cold spot's precise shape, its polarization patterns, and its correlation with other large-scale structures in the nearby universe. If it is a texture or a collision, it should leave specific, subtle imprints on the polarization of the light, a kind of directional fingerprint. Furthermore, if the cold spot is a real physical void or structure, it might also show up as a corresponding underdensity of galaxies in that same direction in the modern universe. Some surveys have indeed suggested a vast, sparse region of galaxies coinciding with the cold spot, a so-called supervoid, though its size and depth are hotly debated and may not be sufficient to explain the full temperature drop. The cold spot endures as one of the most tantalizing anomalies in all of cosmology. It is a ghostly imprint on the first light, a candidate for evidence of something beyond our universe, or simply a reminder that even in a universe governed by statistics, truly exceptional things can and do occur. Its resolution will either anchor us more firmly in our standard model or tear a hole in it, revealing a glimpse of a reality far stranger and more crowded than we ever imagined. The profound cold on the cosmic scale finds a strange parallel in the searing heat of a particle collider, where the building blocks of reality are smashed together to see what emerges. In these violent, microscopic explosions, physicists have glimpsed a ghost, a particle that should not exist. They call it the tetraneutron, a fleeting cluster of 4 neutrons bound together with no protons at all. Its very possibility strikes at the heart of nuclear physics. According to our most fundamental understanding, such an object should be impossible. The nuclear strong force, which glues protons and neutrons together into atomic nuclei, is a social force. It works best in pairs, with neutrons and protons balancing each other's properties. A nucleus made of only neutrons lacks the stabilizing influence of protons, and the mutual repulsion between the identically charged neutrons should blow it apart in an instant. The tetraneutron, a pure knot of neutral matter, defies this rule. The first compelling hints came from an experiment in France over a decade ago. Researchers fired a beam of beryllium nuclei at a carbon target. In the debris of one particular collision, they detected the signatures of 4 neutrons appearing to fly away together, correlated in a way that suggested they had been momentarily bound as a single entity before disintegrating. The signal was subtle and the statistics were low, but it was enough to send shockwaves through the community. Since then, other experiments, including one at the Riken facility in Japan, have reported similar evidence, detecting the telltale 4-neutron correlation with greater confidence. Each new result strengthens the case that for a sliver of time, a billionth of a second, this impossible particle flickers into existence. The theoretical implications of a confirmed tetraneutron are staggering. It would force a major rewrite of our models for the strong force. Perhaps the force can create a subtle, short-range bond between neutrons under extreme, dense conditions that we have not yet fully modeled. Some theorists propose it could be a new kind of nuclear resonance, a temporary, excited state of matter that exists on the very edge of stability, like a soap bubble that forms for just a moment before popping. Others have even more exotic suggestions, involving the particles existing in a tightly packed, tetrahedral shape that allows for a unique quantum mechanical configuration. The resistance from theory is fierce and understandable. Accepting the tetraneutron means accepting that our rulebook for how nuclei hold themselves together is incomplete. It opens the door to other exotic, neutron-only states of matter, potentially even droplets of pure neutron material that could exist in the crushing depths of neutron stars. The pursuit is now a race between experiment and theory. Experimentalists are designing ever more precise collisions, hoping to pin down the tetraneutron's properties, its lifetime, and its exact energy state. Theorists are scrambling to see if their equations can be stretched without breaking to accommodate this 4-neutron anomaly. It is a battle over a particle that may live for less time than it takes light to cross an atom, yet whose conformation would resonate through our understanding of every atomic nucleus in the cosmos. From the ghost of a 4-neutron particle, we turn our gaze to a ghost of another kind, a cosmic structure so geometrically perfect it seems etched by a celestial architect. Drifting over 2,000 light-years away in the constellation Monoceros, the Red Rectangle Nebula lives up to its name, but only in the crudest sense. Through small telescopes, it appears as a ruddy, boxy smudge, but the Hubble Space Telescope revealed its true, breathtaking form. It is not a rectangle at all, but a stunning, symmetrical X-shape, a pair of hollow, cone-like structures emerging from a central hub, connected by what look like delicate, evenly spaced rungs, like a ladder reaching into the void. This is not the chaotic, billowing cloud of a typical planetary nebula, the final shroud of a dying star. This is a structure of eerie order, a masterpiece of precision written in gas and dust. At the heart of this geometric wonder lies a binary star system, 2 stars locked in a tight, aging dance. One is a hot, dying core, a white dwarf, while its companion is likely a red giant, a swollen star shedding its outer layers in a slow, stellar wind. This partnership is the key to the shape. As the 2 stars orbit one another, their gravitational interactions and the outflowing material from the red giant are thought to funnel into 2 opposing cones or jets along the system's polar axis, creating the nebula's basic bipolar structure. Think of it like 2 ice cream cones placed tip to tip, with the stars hidden in the middle where the points meet. The starlight, particularly from the hot white dwarf, illuminates this hollow, conical cavity from within, making the walls of the cones glow with that distinctive red hue caused by a rare form of luminescence from carbon-rich molecules. But the profound mystery, the true anomaly, is not the broad X shape itself. It is those impossible rungs. They appear as a series of straight, parallel dust lanes, evenly spaced like the ties on a railroad track, stretching across the gap between the 2 luminous cones. How does a turbulent, chaotic process of stellar death produce such crisp, repeating symmetry? The prevailing theory is that these rungs are the shadows of dense, concentric rings of dust that orbit the central stars like giant, dark tree rings cast onto the glowing nebula walls. As material puffs out from the red giant in a slow, steady rhythm, perhaps tied to its orbital dance with the white dwarf, it condenses into dust at a specific distance from the stars, forming a new ring with each pulse. We are seeing a fossil record of the star's mass loss, a series of snapshots captured in solid form. Yet, the precise physics that creates such perfectly sharp periodic rings and then projects their shadows with such geometric clarity remains one of stellar astrophysics' most beautiful puzzles. The mechanisms behind the timing, the dust formation, and the stability of these structures are not fully modeled. The red rectangle is thus more than a pretty picture. It is a unique and stringent laboratory. It challenges our models of how dying stars lose their mass in binary systems, demanding an explanation for how nature can achieve such regular, almost mechanical, precision amidst the violent, messy process of stellar death. It stands as a quiet, crimson rebuke to chaos, a demonstration that even in final acts, the universe can craft structures of breathtaking mathematical elegance. Our planet's magnetic shield is not a perfect, smooth bubble. It has a dent, a weak spot where the dangerous heart of space reaches down to touch the upper sky. This is the South Atlantic Anomaly, a vast region stretching from Chile to Zimbabwe where Earth's inner Van Allen radiation belt, a torus of trapped high-energy particles, sags unusually close to the surface. Here, the protective magnetic field is about 30% weaker than expected, creating a kind of Bermuda Triangle in low Earth orbit. For the machinery and people we send above the atmosphere, this anomaly is not a myth, but a very real and persistent hazard. Satellites passing through this zone are bombarded by intense levels of radiation from the inner belt, which can cause electronic glitches, memory upsets, and even permanent damage to sensitive instruments. Astronauts aboard the International Space Station, which orbits through the region several times a day, report seeing strange flashes of light behind their closed eyelids, caused by cosmic rays directly striking their retinas. Mission planners schedule critical spacewalks and system reboots to avoid these high radiation passes, treating the South Atlantic Anomaly as a cosmic storm to be navigated around. The cause of this magnetic hiccup lies deep within our planet, in the turbulent flows of molten iron in the outer core that generate Earth's magnetic field through a process called the geodynamo. Simulations and satellite data suggest a massive reservoir of dense, hot rock sits beneath southern Africa, at the boundary between the core and the mantle. This African large low shear velocity province, as scientists call it, acts like a thermal blanket or a continent-sized dent on the core's surface, disrupting and weakening the upward flow of heat and consequently the convective currents that generate the magnetic field above it. It is as if a hidden mountain range on the core mantle boundary is deflecting the very currents of our planetary shield, leaving a vulnerable patch in the sky above the South Atlantic. This leads to a profound and unsettling question. The weakness is not static, it is growing. The overall strength of Earth's magnetic field has been decreasing for centuries, and the South Atlantic Anomaly is both the epicenter and the most dramatic symptom of this decline. The region of weak field is expanding westward and splitting into two lobes, further complicating the radiation environment. Such a sustained, dramatic weakening is precisely what scientists would expect to see in the early stages of a geomagnetic pole reversal, a process where the planet's north and south magnetic poles swap places. In the geological record, these reversals are common but chaotic, happening every few 100,000 years on average. The last full reversal was about 780,000 years ago, meaning we are long overdue. The process is not instantaneous. It could take 1,000 years or more. During that time, the magnetic field would become complex and multipolar, potentially splitting into many weak poles all over the globe before re-establishing a stable, reversed configuration. The world would not end during a reversal, but the consequences would be significant. A severely weakened magnetic field would offer far less protection from solar and cosmic radiation. This could lead to increased rates of cancer, damage to power grids and satellite fleets on a global scale, and potentially alter atmospheric chemistry. The South Atlantic Anomaly gives us a sobering preview of what a planet with a faltering magnetic shield might look like for our technology-dependent civilization. Whether the current changes are the prelude to a full reversal or just a temporary fluctuation in the dynamo's chaotic rhythm is one of the most urgent questions in geophysics. We are left watching this growing dent in our sky, a silent, spreading vulnerability that reminds us our planet's protective heart is alive, restless, and capable of profound change. The final frontier of cosmic anomalies lies not in what we see, but in what our equations dare to dream. General relativity, the theory that gave us black holes, also contains the seeds for their bizarre theoretical opposites. Imagine running the film of a black hole backward in time. Instead of an event horizon from which nothing can escape, you would have a boundary from which nothing can enter. Instead of a bottomless pit consuming all matter and light, you would have a cosmic fountain, eternally spewing out material that had been trapped since the beginning of time. This is the white hole, a perfect mathematical mirror of a black hole within Einstein's field equations. While mathematically permissible, physicists consider white holes to be physically improbable freaks of cosmic history. The second law of thermodynamics, the universal rule of increasing disorder, stands firmly in their way. A white hole would represent a massive, sustained decrease in entropy, a violation of time's arrow on a cosmic scale. Furthermore, for a white hole to exist in our universe, it would have had to be born in that exotic state at the moment of the Big Bang, a pristine and perfectly coordinated eruption that has somehow avoided being contaminated by any infalling matter for over 13 billion years. Any single particle of dust falling into it would collapse the entire structure back into a black hole. So while they tantalize as theoretical curiosities, white holes are generally seen as cosmic phantoms, beautiful solutions to equations that reality itself has likely forbidden. But if one ghost of relativity is forbidden, another offers a tantalizing, if fragile, promise of connection. These are wormholes, often called Einstein-Rosen bridges. Picture the fabric of spacetime as a vast sheet of paper. To get from a point on one side to a point on the other, you would normally travel across the entire surface. But if you could fold the paper so the 2 points touch, you could punch a hole through the connection, creating a shortcut, a tunnel through the higher dimension that bypasses the long journey across the sheet. This is the essence of a wormhole, a theoretical tunnel with 2 mouths connected by a throat, linking 2 distant regions of space, or perhaps even 2 different points in time. The mathematics of general relativity allows for such structures, but they come with a devastating catch. The throat of a naturally occurring wormhole would be incredibly unstable. It would pinch shut the instant anything tried to pass through, like a bubble collapsing faster than light could traverse it. To hold the throat open, to make it traversable, our equations demand the presence of something truly bizarre, exotic matter. This is not antimatter or dark matter. Exotic matter would need to possess negative energy density, creating a kind of anti-gravity that pushes the walls of the tunnel apart against their own crushing desire to collapse. While tiny amounts of negative energy can be produced in lab experiments through quantum effects like the Casimir force, the quantities needed to stabilize a wormhole large enough for a person, let alone a spaceship, are astronomical and almost certainly impossible. This is why wormholes remain firmly in the realm of theoretical physics and science fiction. They are a reminder that our most profound theories of gravity do not forbid cosmic shortcuts, but they do demand a price for them, a form of matter that may not exist in the necessary amounts anywhere in our universe. They stand as the ultimate speculative anomaly, a symbol of our desire to conquer the vast distances of the cosmos, bound by the unforgiving fine print of physical law. We have traveled from the drifting paths of forgotten spacecraft to the cold, ancient scars on the first light of creation. Each of these 25 cosmic glitches, from the silent acceleration of Oumuamua to the perfect geometry of Saturn's hexagon, is more than a puzzle. They are pressure points, places where the smooth story of the universe meets a crack. Each one represents a frontier of our own ignorance, a glowing signpost pointing toward physics we have not yet written. They are not failures of our science, but its most vital fuel. Every unexplained drift, every missing particle, every impossible shape is a potential key, waiting to turn in a lock and open a door to a deeper layer of reality. The true revelation of this journey is a humbling and exhilarating one. The universe is not just stranger than we imagine, it is stranger than we can imagine, constantly performing feats that defy our neat categories and comfortable laws. Our greatest theories are not wrong, but they are clearly incomplete, sketches of a masterpiece whose full dimensions we are only beginning to trace. So we are left with a question for you. After this voyage through the anomalies of space and time, which cosmic glitch reshaped your mind the most? Was it the haunting silence of the wow signal, the eerie order of the red rectangle, or the terrifying possibility of the dark flow pulling us toward another universe? Let us know in the comments below. If this exploration into the unknown captivated you, please give this video a like and subscribe to the channel. Your support helps us continue these deep dives into the mysteries of the cosmos, because the next great anomaly is out there waiting to be found.